All right, my AP Chemistry kids. We're going to finish up Chapter 9 just a little bit on some multiple bonding. So you can try this on your own, see if you can remember how to do this. So pause the video and we'll go over it once you're done. Just restart the video. Okay, so if you are looking at HCN, when you do the Lewis structure, it would end up being a single bond between the hydrogen and carbon, triple bond between the carbon and nitrogen. Electron domain geometry, so we're focusing on the central atom here, and that would be the carbon. Electron domain geometry is, there's only 2 electron domains, so that would be linear. Molecular geometry, same, it's going to be linear. Molecular polarity, so now you would look at your electronegativity charts and carbon versus nitrogen. It is a slightly polar molecule. This is actually acidic because of that. Hybridization on the carbon, since there's 2 electron domains. Remember, hybridization is about electron domains. Since there's 2 electron domains, that means we would need 2 hybrid orbitals. Therefore, 2 atomic orbitals are needed. So you start with your S and 1 P, and that will give you your 2 atomic orbitals. So it's going to be an SP hybrid. Ooh, sorry, my cat's right here. Girl. So there will be 1 sigma bond, or actually 2 in the whole molecule, 2 sigma bonds, 1 between the carbon and nitrogen, 1 between the carbon and hydrogen. And then number of pi bonds would be 2 because you have 2 additional bonds to make that triple bond. So there you go. Okay, let's move on, just kind of review a little bit. Sigma bonds, that's when you have the head-on overlap between the electrons to make that first single bond. And all single bonds are sigma bonds. Pi bonds, electron density, that's when you have your sigma bond, but then you have that side-by-side overlap to make electron density above and below the bonding plane. And there's 2 types of multiple bonds. Double bond, which is 1 sigma, 1 pi, and a triple bond, which is 1 sigma and 2 pi bonds. And anything that's left over is we have unhybridized p orbitals, and we're going to talk about those a little bit. Okie dokie, we saw this before. So this is just a visual of what a pi bond looks like. It is 1 pi bond. So this slow, remember these are 1 p orbital, 1 p orbital. 2 orbitals means 1 bond, even though there's 2 regions the electron can potentially exist in to make that bond. We started with this, C2H4. If you draw the Lewis structure, you see that there is a double bond here between the 2 carbons. And if we were to do the electron domain geometry, 1, 2, 3, that would give us 3 hybrids that we need, therefore 3 atomic orbitals, therefore sp2 hybrids on each one of these carbons. So if we're doing the sp2 hybrids, we've only hybridized 2 of them. That means we have 1 p orbital left over. So 1 sigma, 1 pi bond, that's double bond. Both are sp2 hybrids. Trigonoplanar because it's an sp2. And a little bit more detail. So this is what it looks like. It's beautiful. So what we have here are sp2 hybrids on the carbons, and it's a visual of that unhybridized p orbital. sp2 hybrids and the unhybridized p orbital. So the multiple bond comes from the overlap, and it's not showing the overlap just because of the space, but these are overlapping in space to give that pi bond. So the electrons can exist above and below the plane in that double bond. So, sigma bond, pi bond. Okie doke. We talked about this a little bit already. Sigma bond, pi bond. And this is just a better visual. So we said this one part isn't showing. Where's my mouse again? There we go. Get to that. So this isn't showing this overlap, but this is a much better representation. They do overlap and kind of pull at each other to share that electron density to make the double bond. So you have your sigma bond and your pi bond. Okie doke. What about CH2O? Can you give the electron domain geometry, molecular polarity, hybridization on the carbon, sigma bonds in the molecule, pi bonds in the molecule? And it looks like this. I would encourage you right now to pause the video and answer those questions and then start the video to see how you did. Okay, assuming you have done the problem, let's go through and look at that carbon. Electron domain geometry, we have 1 to 3 regions. So let's just make that a little bit more visual for you. So we have 1, 2, sorry, my cat just jumped on my lap again. Do you want to say hi? This is Dixie. Want to learn chemistry with me? All right. So 2, and then where'd my mouse go? Dixie, maybe it was my mouse. Where is it? Ah, there it is. Okay. And then 3, electron domain geometry. Sorry about that. This is my laugh. Molecular geometry. So electron domain geometry with 3 would be trigonoplanar. And the molecular geometry, there's no bonds on or lone pairs on that carbon, so it would also be trigonoplanar. Molecular polarity, definitely, because that my mouse keeps moving on me. That oxygen's highly electronegative, so we have a dipole towards the oxygen. And the hybridization on the carbon, since its electron domain geometry is, there's 3 of them, it's sp2. We have 3 regions, we need 3 hybrids, and we get 3 hybrids by doing an S and 2 Ps, sp2. Total number of sigma bonds in this molecule will be 3, and number of pi bonds will be 1. There you go. Alrighty, let's take a deeper look into our multiple bonds. So this is that CH2O. There's that pi bond, and the sp2 hybrids on both the carbon and the oxygen. So that was our Lewis structure, and this is what it looks like in 3-dimensional space. Keep going with our triple bonds, because with a triple bond, you're going to have 2 unhybridized p orbitals. So if you take a look at C2H2, and there's a little different in your notes because this image was better. So here we have a triple bond between our 2 carbons. So each carbon, if you look at its electron domain geometry, it has 2 electron domains, therefore 2 hybrid needed, therefore 2 atomic orbitals, so we have an S and a P. So these would be our sp hybrid, sp hybrid, sp hybrid, sp hybrid. So since we've hybridized only 1 p orbital, we have 2 unhybridized p orbitals on each carbon. And that causes the triple bond to happen. All right. Now that's, there's 2 different types of multiple bonds. There's localized bonds where they are stuck between 2 atoms. So if you take a look at C2H2, the multiple bonds, the electrons in that triple bond, there's nowhere else for them to go. They are going to be stuck right there. But when we have resonance structures, then the electrons move between additional atoms. So this would be a localized bond, HCN. The electrons are stuck between the carbon and the nitrogen. Versus delocalized. So the electrons can move between multiple sets of atoms, not just 2. So in the case of benzene, we can look at this, and there are 6 carbons and 6 hydrogens. And on each carbon, if you take a look, it's going to have 3 electron domains, so therefore an sp2 hybrid. But we also know that there's 2 resonance structures. You could have the double bonds alternating this way or this way. And we've briefly talked about it in class. You could also represent it this way because the electrons pretty much are flowing between the 2 resonance structures, and you're going to learn why today. So when we look at that, we see that each carbon atom is going to be sp2 hybridized because it has 3 electron domains around it. It has the single bonds between both carbons and the single bond with the hydrogen. Since it's sp2 hybrid, what is not involved in the sigma bond is going to be the unhybridized p orbitals. And each carbon has 1 unhybridized p orbital, and they are above and below the plane. So when we are drawing or representing benzene, we do that Lewis structure. Let's see, we were doing it, here's a double bond, here's a double bond, here's a double bond. Or we were looking at it the other way, the other resonance structure. Let's see, let's do purple because that's my favorite color. We were also saying, well, instead of that way, we could have the double bond here and here and here. 2 different resonance structures. But the data doesn't show that that actually happens. So what is actually going on here with this structure? So there you go. This is a better visual. So you can have localized bonding. So either the electrons are here, here, and here, or here, here, and here. But what we find is that in the lab, we don't have 2 different types of bonds. We actually see that So if you did a resonance structure, you'd see a double and a single bond. You'd see a short bond and a long bond. You'd see a strong bond and a weak bond. But what we actually see is that all the bonds are equal. So what we really have figured out is that the electrons aren't stuck between two. There's this overlapping cloud above and below the plane that is basically a river of electrons. They can move freely between all of these p orbitals, both above and below the plane. So they're delocalized over the entire ring. So that's what I was saying. Experimentally, they're all the same type, so that's how we figured out. It's actually just what we call delocalization, not resonance. Delocalization. A couple of things. Let's see. We all know that they're going to have two atoms with two electrons. That's your sigma bond. Shared between the same axis. And then we have our pi bonds, where the second and third pair of electrons have to be shared with our unhybridized p orbitals. When you have resonance, delocalization is also possible, like we saw with benzene. Alrighty, we're almost done. So bond order. Bond order is a way for us to measure the total number of bonds. And when we look at bond order, we can also relate that back to bond length and bond strength. So the higher the bond order means more bonds you have between two atoms. So be a stronger bond and shorter bond. So for bond order, it's really straightforward. If you calculate it and it's 1, that means a single bond. If it's 2, it's a double bond. If it's 3, triple bond. And we don't have quadruple bonds, so be careful. And a thing to note is that when you have resonance, it's possible to have fractional bond orders. How do you figure out bond order? It's very, very simple. You just basically draw your Lewis structure or structures and take the total number of bonds you see between two atoms in all of the resonance structures and divide it by the total number of resonance structures. Even if you have no resonance structures, you just divide by 1 because there's one structure. So let's do an example. Determine the bond order between the first and second oxygen atoms in ozone. So what we have here is we're going to be looking at this oxygen atom and this one. So let's go ahead and do that. So this would be the two that we're looking at. And then these two right here. So same two atoms, two different resonance structures. When you go through and look at them to figure out the bond order, you're going to take the total number of bonds you have between these atoms. So we have 2 here and 1 here. So we have a total of 3 bonds between those two resonance structures. So you go ahead and just do it. 3 bonds divided by 2 resonance structures gives you a bond order of 1.5. What does that mean? That means that you pretty much have 1.5 bonds between those two atoms, and it's going to be stronger than a single bond, but weaker than a double bond. It's going to be shorter than a single bond, but longer than a double bond. So at this point, let's go ahead and have you do sulfur trioxide and carbon dioxide. Draw the Lewis structures, including resonance, although with carbon dioxide, remember, those other two resonance structures aren't valid. Determine the total number of sigma and pi bonds in the molecule and the bond order of each bond. So again, pause the video and try these 2 examples, and we'll go over them in just a sec. Okay, so if you went through and did these 2 examples, let's look at sulfur trioxide. When you draw the resonance structures, there's actually 3 of them. And so if you're going to go through and do the bond, or this is the sigma bonds and pi bonds. So if we're looking at this, remember every bond is a sigma bond. So 1, 2, 3, only one of those. So 3 sigma bonds. And then we do have a multiple bond here. So that's going to be your 1 pi bond. So 3 sigma, 1 pi. And then all of the oxygen atoms have the same exact kind of electron environment. So we'll just do the bond order between a sulfur and an oxygen, and then that applies to all of them. So bond order, you have 4 total bonds. So if we were taking a look at this one, there's 1, then we have 2, and then we have 3, 4. There's your 4 bonds, and there's 3 different resonance structures. So you have a bond order of 1 1/3 pretty much. For carbon dioxide, our only valid Lewis structure is double bond. Again, I think of in and out every time I say that. And if you do the sigma bonds, there's 2 sigma, 2 pi's, and a bond order of 2, double bond. And both carbon oxygens have the same kind of electron environment. And we are done. Thank you very much.